right one. So again, we want I to start at 1 and just go to n. And this time you have a more interesting expression, but the same kind of thing. You have 6i over n, only now we want to square that, then add, that's not a square, then add 5 times 6i over n, then add, I believe, 7, then that quantity, which is all representative of your function value, your f of x value, gets multiplied times the x value. And of course, this could even be distributed, so it could be disguised. It didn't have to look like this in a factored form, because if you distributed 6 over n to each of these, you'd still have a valid expression, and then it would be more challenging, of course, to figure out what was the function that this represented. But theoretically, we could do that too. So if we call our original function f of x again, and this represents what we did to f of x to create the heights of our rectangles, then the real question is, what's the purpose of the 5 and 7, and what are the 6n's doing, or the 6i over n, sorry. The 6i over n are working the same way as the 10i over n, so this is the x, and so you have x squared plus 5x plus 7. And it turns out once you've done a couple of these, you say, well, I've just pulled out the information I need and substituted x. Now what I overlooked, I was supposed to write as part of the answer. This is called an indefinite integral because we haven't said how far we're going to create an area. This does say how far we're going, however. This is a definite integral because we know how far we're going based on the fact that this number is 10. Now, if we're starting at 0, we would go to 10. But if we're starting at 5, we'd go to 15. So we also still have to decide, well, what was the starting point? This is the information we need to decide that. If I goes from 1 to n, it's a right-handed limit. If it went from 0 to n minus 1, it would be left-handed. And the fact that this starting at 0 produces, and notice we wouldn't want this to say n if we were doing left-handed. But if this started at, well, if it starts at 1, we know we're starting this next to 0. That tells us that we want to go from 0 to 10. If we wanted to create a value here that would make this start at 1 or 2 or 5 or 100, we could do that, but it would change the way the formula was set up also. Okay, so based on that, what is this going from? 0 to 6. What is that telling us? That if we were to look at the curve of this is a little more familiar than this function maybe, but this parabola, we're saying we only want to look at the area under the parabola that goes from 0 to 6. And by the way, that's interesting because this parabola does not open down, which would be the most obvious case or easiest case to look at. It opens up. So you would have to say, I need to know where that parabola is, because maybe we're talking about an area under the curve that is going to be like this, and then a negative area, and then if this happens to be 6, and I haven't tried to figure out where this graph is, by the way, but maybe it's something like this, then we're going to have to figure out an area here, and a negative area here, and combine those in order to figure out the area we want. Hopefully it's not that messy if you had to do the problem, but it could be. Okay. Obviously, if it were if the vertex were above the x-axis, then all the area underneath, you would just draw vertical lines 0 and 6, and you could calculate the area underneath that. Okay. But the fact is, the assumption based on the way this is constructed is you're always working from what? The x-axis. And if you're above it, you're talking a positive area. If you're below it, you're talking this strange new feature called a negative area, which just means you have to account for negatives when you do it. Anyway, that's a little more information than you needed for this problem. But that's what this represents. Okay? Now, that was the only thing she asked me to go over on this worksheet. And since I haven't worked problems 1 and 2, but she did attach to me, I don't know what she gave you, because she gave me this the other day, a very nice derivation of proving that the problem 3 Riemann sum. So you got that?
Mm-hmm.
Hopefully yours is a little easier to read than mine, because I can barely see
No,
this.
it's the same.
Okay, but anyway, I looked through it, didn't find any errors, but then I didn't work it myself, so who knows. Okay, the next thing we're supposed to do, and she just told me this evening, so I'm not sure if I'm doing this right. I'm guessing now's a good time to start the attendance sheet around, because most